Welcome to part 3 of video on per unit systems. So I have made two videos prior to this, per unit system part 1 and part 2, in which we are primarily working on one phase circuits. And then I got a lot of comments and some request for how to analyze, how to make a per unit system representation of a three phase circuit. So that is a subject for this video, and the concept is same, the idea is same, that using per unit system we are able to simplify the calculations. Wherever there are transformers, we are able to represent it in a more simpler form and at a common voltage, so that we are able to solve the problem. So that the concept is same, but you need to do a little bit of adjustments and a little bit of corrections when you're studying a three-phase circuits. So let's get started with that. So let's begin by comparing the first of all the base, per unit base. So you know that for a per unit system we require S base, that is base power, and then you require base voltage, and then base current, and then base impedance. And you already studied that. Let's denote a base as SB and base voltage as VB. Now here I am not mentioning the units, so this may be in megavolt amperes, this may be in kilovolt amperes, this may be in volt amperes or whatever. So mainly it should be voltage into current, and it could be in different units. Similarly, V base can be in kilovolts, it can be in simple volts or megavolts or whatever. And while calculation, you should take care about the units, the multiplicity of the units. You should take care. You already seen that in previous videos. Now, what is base current? Base current is IB, and the formula wise, if you see, IB will be nothing but SB divided by VB. Now you might have a doubt: isn't IB conjugate is SB and VB? So these are all base quantities. These are all actually real numbers. They are not complex numbers. They are all simple real constants. So it is like this. And what is Z base? So Z base is nothing but V base by I base. Or another formula you can use, that is V base square by S base. So basically substituting this into here. So this is about the base quantities, and you already studied this. All this is one phase. Now what happens if I now move over to a three phase system? So let's use a different color. Now the notation, I'll say S base three phase. Now what is the relation between S base here and S base three phase here? So strictly speaking, there is no relation, because the one phase problem is a different problem and three phase problem is an independent problem. So you don't have to have these two related in some way. However, for the same problem, I want to consider both. Then these two will have a relation. So this is one phase quantity. So one phase power, you always know, in a balanced system will be one third that of the three phase power. So that is it. So here let's come to V base. So in a three phase system, what is the base voltage? So the base voltage you should always consider as a line to line voltage. So if a because if a three phase system is given and somebody says the voltage of a three phase system is 20 kilovolts, the 20, by default it is a line to line voltage, it is not a phase voltage. So this is the line to line voltage. And for the same system, if you want V base, so the relation will be again, you have to divide by root 3, because a single phase voltage and line to line voltage are related by a factor of root 3. I'll write down those relations later below. Now what about I base? So now we need to always consider the line currents. So I base line currents. So in a three-phase system, you know that there will be a phase current and there will be a line current. These are different. However, if you consider a star system, star connected system, then the line current and phase current are all equal. So they are nothing but this one. Now what is the relation between these three? So the relation between these three is, so S base 3 phase is nothing but root 3 into V base line to line into I base line. So from this, if you know this and this, I can calculate this and so on. Now coming to Z base. So what is Z base? 3 phase. Now Z base 3 phase will be, what is the base impedance for a 3 phase system? So I can, because it's a phase system, I can use the phase quantities, or I have to convert this line quantities to phase quantities and so on. So that's what I'll just quickly do it here. So you see, Z base 3 phase will be nothing but V base line to line divided by root 3 will give me the phase voltage, and this divided by the phase current. So phase current will be I base line. So because the voltage is divided by root 3, that means it is a star connected system. So therefore the line to line current itself is the phase current. So I can go by this. Now I can also introduce the power into this. So what is I base line? So look at this first equation. From this I get what is I base line. This implies that I base line is nothing but S base 3 phase divided by root 3 V base line to line. So this, if I substitute here, so I'll get V base line to line by root 3 multiplied by, this is 1 by this one, so I just reverse this. So root 3 into V base line to line divided by S base 3 phase. Now root 3 cancels out each other, and then finally you get V base line to line square divided by S base 3 phase. So this is what base impedance of 3 phase system. Let's compare it with base impedance of a 1 phase system. So what is base impedance of a 1 phase system? It's nothing but V base square by S base. So if you compare these two, so base impedance of 1 phase system and base impedance of 3 phase system, the formula is similar, whereas here you use the line to line voltage, here you use the phase voltage, and here you use the 3 phase complex power, and here you use a single phase complex power. Now we can also relate these two things. So that is, if I want to convert this into line, so what is base voltage per phase? So if I can take V base line to line, and then I can divide by root 3, and then I can just maintain the square above. Similarly, what is the single phase power? That is 1/3 of 3 phase power. So divided by 3. Now if you see, the square and root 3 will become 3, and then there's also divided by 3. It will get cancelled out each other, and you will get V base line to line square by S base 3 phase. So finally what you concluded is these two are actually equal. So that is a surprising thing. So for a 3 phase system, Z base is equal to Z base line to line, or sorry, Z base 3 phase. So the base impedance is same whether it is a single phase system or a 3 phase system, and the value I can use either single phase voltage, or I can use line to line voltage, that is V base line to line square divided by S base 3 phase. So this is again quite convenient when you're working in a 3 phase system. Alright, so I have given a lot of theory here, a lot of derivation and stuff like that. But let's take up a series of problems, and via solving these problems, your understanding will be even improved. So let's do that. So I have written two problems that are there in front of your screen. That is, problem 1 and problem 2, they're exactly same except there is a small variation with respect to the first problem as a three-phase problem and the second problem as a one-phase problem. So let me read the problem. A three-phase 400 MVA 20 kV generator has a winding reactance of J 0.8 ohms per phase. Represent the generator in per unit. Okay. Similarly, the second question, a one phase everything else is same. 400 MVA 20 kV generator has a winding resistance of J 0.4 per phase. Represent the generator in per unit. So strictly speaking, there won't be a one phase generator of 400 MVA and 20 kV and all this thing, but just as a theoretical concept, uh, you can consider it as a voltage source, a one phase voltage source with a winding resistance of J 0.8 ohms and all. Now, when I say represent the generator in per unit, and here also represent generator in per unit, the first thing you should say is answers to P1 and P2 are same. So this is a true or false. So just ask yourself, if I solve the first problem, I get some answer. For problem second problem, I get some answer. Is that both answers same? So that is a question. Where is it same true or both will have a different answer? False. You pause a bit. You read the questions. You think about what will be the answer, and later on we'll compare our answers. So let me begin by solving the first problem. So it's a three-phase system. So therefore, 400 MVA would be the base, that is a three-phase base, and 20 kV would be the line-to-line voltage. So therefore, if I go down, so solution for first problem. So S base three-phase will be 400 megavolt amperes. Similarly, V base line to line would be 20 kilovolts. So under this system, what would be my Z base? So that is, this is a three-phase system. So what would be my Z base? Z base will be V base line to line square divided by S base, three phase. So that will be equal to V base line to line square will be 20 kV square divided by 400 MVA. So this kilo and then mega will cancel each other, volt will cancel each other. There will be one more volt, so volt by ampere will be ohms. So we get 20 square by 400. So 20 square itself is 400. So 400 by 400 will be 1 ohm. So this is my base impedance. And therefore Z per unit will be nothing but Z actual divided by Z base, three phase. So that will be J 0.8 divided by 1. So that will be J 0.8 per unit. So this is the answer for the first problem. Now look at the second problem. A one phase 400 MVA 20 kV generator has a winding resistance of, so when I say it is a one phase system, so this 400 MVA is actually the base per unit base. So that is S base itself is 400 MVA. Similarly, V base will be 20 kV for the generator. So here I'm not having to mention three phase or line to line because it's already in one phase. So therefore, what will be my base impedance? It will be exactly same. That is V base square by S base. So that is 20 kV square divided by 400 MVA. So this will be directly 1 ohm, same as before. And therefore Z per unit will be J 0.8 ohms, the actual impedance, divided by 1 ohm. So ohms will cancel, the unit will cancel. So I'll get J 0.8 per unit. So what is the diagrammatic representation? So answer 1 and answer 2, you have a generator. So you will represent the, because answer 1 is a three-phase system, you represent as the equivalent one-phase system. So there is a generator and then there is a impedance of the generator or reactance of the generator, and this is J 0.8 per unit. Similarly, here also you have a generator. This is only a one phase generator, and then this will be J 0.8 per unit. So this is how it turns out to be. So this is one phase equivalent of a three phase system. This is already in one phase. So this is one phase equivalent. And this is uh, already in one phase. So, so if I go back, when I say whether what is the answer to the above, so it's actually true. So the answer is same. All right. So I'll give you some time to think about it. You can pause for a while. Meanwhile, I'll prepare the next question, and we are going to solve that next question. Okay, so now we have another problem, that is a third problem for this video. So look at this problem, try to read this problem, and try to attempt to solve this problem. You can pause once we complete reading this problem. You can try the answer, and then you can compare the answer with what I get it. So what is there? A 440 volts three phase three wire transmission line has impedance of zero point 0.2 plus j zero point 0.4 ohms per line. So each line in the three wire system has this impedance. Now this 440 volt would be obviously the line to line voltage. So anywhere a three phase system voltage is being talked, unless it is specified, you can safely assume that the voltage is between the line to line. At the end of the line, so at the beginning of the line, what is there? Nothing is given. But at the end of the line, two three phase loads are connected in parallel as follows: load 1 and load 2. Load 1 is star connected 5 plus J3 ohms per phase, and load 2 is delta connected 6 minus J6 ohms per phase. The question is, represent the above network as a one phase per unit equivalent. Of course, I think the question is incomplete. Let me just add some more points here. Taking So S base as say 20 kVA and V base as 440 volts. So this is S base three phase, okay, and this is also V base three phase. So this is all three phase. So even if this are not mentioned, you can assume that it is this one. So taking S base as 20 kV and V base as 440 volts represent the above network as a one phase per unit equivalent. So this is the question. Try to address this question. As you see, this type of questions you won't find in typical textbooks. So this is a question generated by my own thought. So try to attempt it. So and then we'll see how it comes. Whereas now I'll do my own solution for this. Let's do that. So what I'll do is just for our convenience, I'll draw the three phase circuit. Although that is not asked. What is asked is one phase per unit circuit. So let's draw three phase actual circuit. So there is a transmission line with some impedance. There is another transmission line with some impedance. There is another transmission line with some impedance. I'm sorry. So actually this is lumped and short at the beginning, but this resistance and reactance are all spread out throughout this transmission line. Okay, so what is the value? So if I go up, 0.2 plus J 0.4. So this is 0.2 plus J 0.4 ohms. This is not in per unit, this is actual ohms. All right. So then it has two loads, star connected load and delta connected load. So let me draw the loads. So the first load is star connected. So let me use a different color. This is a star connected load. So I'll connect this one to the first line and this one to the second line. Sorry. And this one I connect to the third line. Parallel to this, so here what is the impedance? 5 plus J3 per phase. This is ohms per phase. Now, what is the other impedance? The other impedance is delta connected. So again, I'll just connect it in parallel to the first one. All right. So here the impedance is 6 minus J6 ohms per phase. So this minus indicates there is a capacitor here. So this is the system that is given to us. So as you can imagine, this is very cumbersome and long process to draw this because it's a full three-phase system and all. So represent the above network as a one-phase per unit equivalent. Now I can just look at the structure of this and I can actually represent a one-phase per unit system. So let's draw one phase per unit system, but then the values we will have to calculate. So now without values, so I have source impedance and then I have two impedances. That's it. So this is my one phase per unit system. So I'll be filling the values later here. So let's get back. So what is the S base for this system? S base is 20 kilovolt ampere given in the question, and then V base is 440 volts. Okay, so one thing is straightforward. What you can do is you can take the voltage base and you can take these two and then calculate the Z base. So Z base is nothing but V base square. This is line to line, and then S base three phase. Or I can take it. So already we had just derived this. So this is 440 square volts square divided by 20 kVA square. Sorry, there is no square for this. 20 kVA. So this is 440 into 440 by 20, and units anyway it comes out to be ohms. So the unit is ohms. But what is this value? So let me switch to my calculator. So this is my calculator. 440 square divided by 20 kVA. So of course here I'll use 20,000 because it's voltage and all. So I'll just use 20,000. So I'm getting 8.8 ohms. So 8.8 ohms is my base impedance. So therefore Z per unit for the line. So actual impedance divided by Z base. So the actual impedance is J 0.2, sorry, 0.2 plus J 0.4. This will get divided by 8.8. So 0.2 by 8.8 and then 0.4 by 8.8. So 0.227, 0.0227 plus J 0.454. So I think, yeah. So this is my per unit impedance of the transmission line. So this I can right away make an entry here. So I already calculated this. This is 0.227 plus J 0.0454. Okay, so this is in per unit. Now, what about this one? So you look at the calculation. So here the it's already star connected and 5 plus J3 is there. So I can right away represent it as Z per unit of load 1. So since it's already star connected, I can take same thing. So 5 plus J3. Let me just check the value. 5 plus J3. Okay. So divided by 8.8. So 5 by 8.8 and then 3 by 8.8. 0.568 plus J 0.341. So this is my per unit impedance. So here I can write it the values 0.568 plus J 0.341 in per unit. Now here what I want to do is, because this is given in delta connection, I cannot directly apply this formula, because in delta connection the line current and the phase current are different and some things are different. So what is the equivalent star for this delta? So we all know that from star delta transformations that we have studied in circuits, that any delta system can be represented by equivalent star system if I simply divide the impedance by 3. So, so 6 minus J6 by 3 will be equivalent star impedance. So that is what I'll do it. So Z per unit for load 2 will be 6 minus J6 divided by 3 to convert. So load 2 equivalent star impedance is nothing but 6 minus J6 divided by 3, that is 2 minus J2 ohms per phase. So that's what I'll use it here, and then 8.8 if I connect. So this will give me the correct comparison. So that is 6 divided by 8.8. So that is 0.682. I'll round it off. So 0.682. So this is minus J 0.682 per unit. So now if I go up, I can solve this. So here 0.682 minus J 0.682 per unit. Now if a question is asked, what is a current? So you can, from this solving this circuit, you can always find the current. But you should be careful about one thing, that this V base is line to line, so you have to divide by root 3 and all. But anyway, so whatever is required, that is the one phase per unit representation of this big circuit can be done as this one. So I hope you understood like how to handle star and delta in this. So let's do some more problems on this. I think I have one more problem on this, and then we'll see. Okay, so we now have another problem, and this problem is again generated from my own thoughts. So, but then similar problems you can find somewhere in the some of the textbooks. But then this is slightly complicated version, and I hope it covers all the uh, minor issues or minute issues come when coming to representation of a three-phase transformer with delta star connection or star delta connection and so on. So this problem is nice in the sense that it has all the uh, good sufficient complicated things for doing a three-phase to one-phase per unit representation. Let's begin by looking at the question. So obtain the reactance diagram for the system below. So I want to get a reactance diagram for this system. And then what it has. So at first it has a generator. It is a three-phase generator. 18 kV is the rated line-to-line voltage for this generator, and 100 MVA is the base or the rating of this generator, with X is 8%, 8% reactance. This generator, three-phase generator, is followed by this one. So this is actually not a one single transformer. There is actually three one-phase transformers. Each one is rated at 40 MVA. So if there are three transformers, each transformer is 40 MVA. So total capacity of transformation that we have here is actually 40 into 3, that is 120 MVA. So the generator is at 100 MVA. So even if the generator is operating at full, I'll be able to transfer the power from this side, because I have the capacity of 120 MVA here. And this 20 by 150 kV is the voltage transformation ratio. So this is each single phase transformer. So that means the one leg of delta here and one leg of star here have this ratio of 20 into 150 kV. So every time I say when it's a three-phase transformer, the voltages are line voltages, but then one-phase transformer is mentioned here. Therefore, this 20 and 50 are the phase voltages connected in delta star, and then the per unit reactance is 6% for each of these individual transformers. Now, you can also get another doubt that while the generator is rated at 18 kV, the transformer is 20 kV in the delta side. So how does it match? 18 and 20 are not matching. So it's always possible like that. In fact, purposefully, this problem has been created such that we have such cases covered. And this 18 kV is the rating for the generator, and 20 kV is the delta side voltage of the transformer. And then we have a transmission line. There are actually three lines. This is a single line, but then there are three transmission lines. Each line will have a reactance of 80 ohms. On the other side, so now the question is, what is the voltage of this? So that we'll come to it, we'll do the calculation. On the other side, there is a star delta transformer, but then this is not a one single transformer. There are three individual one-phase transformers, each 30 MVA. So total I have a capacity of 90 transformer here with each 30 MVA. Next, we have a bus here, and then there is a three-phase load, and the rating for the load is 24 kV. That means the line-to-line voltage for this three-phase load should be 24 kV. And it is also mentioned that it's actually 24 kV, the voltage at this bus. And the load is 40 megawatts, and then at 0.9 power factor lagging. Alright, so here some more information is given. Take the system base of 100 MVA and then voltage base of line to line of 24 kV for the load. That means the base quantities are defined for the load, and from that we need to go ahead and solve this problem. So I would like to pause here. You can pause here and then try to attempt this problem, and then later on you can compare your answer with my answer. So I'll solve this problem right away. So I'll begin by making a copy of this question. So I'm just making a copy of this diagram. Let me just delete this area. Okay, so I have this system now, and already it is mentioned that the base voltage should be 24 kV for the load. So let me begin by marking that region. So this is my region, and within this region, so voltage base is 24 kV, and remember that it is a three-phase voltage base. That means it is a line-to-line voltage base for this. And what is S base? S base is 100 MVA for the entire system. So this is also three-phase. So that also I know. Now the question is, should the transformer T2 be inside this region or should the transformer T2 be in the other region? So as the way I defined here, the transformer T2 is outside. So let's define one more region as something like this. So I use a different color and this is my next region. So this region comprises of the transformer and the transmission line. Now the question is, what is the base voltage for this particular region? So look at the transformer here. So the base is 24 kV and the 24 kV is on the delta side. That means each leg here is 24 kV. Now what is the turns ratio? So turns ratio is right side part is low voltage and left side part is high voltage. So in order to get the voltage here, so or let me just draw the diagram. There is a star part and delta part. So this star part, so this is transformer T2. This is 24 kilovolts and the ratio is 160 by 30. So therefore, what is the voltage induced in each of the phases here? So that will be nothing but 24 multiplied by 160 divided by 30. So this much voltage will come in each phase here. But then if I want to know the line voltage, because here it's already the line voltage. What is the line voltage on this side? I have to multiply by square root of 3 to get the line voltage. So this is line voltage of HV side of T2. So that is this calculation. So 120 kilovolts into 160 kilovolt by 30 kilovolt into root 3. So you should be clear why we are doing this root 3. Because it's delta to star, so I'll be getting the factor of root 3. So let's do this calculation. I will go to calculator. So 24 multiplied by 160 divided by 30 and then again multiplied by square root of 3. So I'm getting 221.7 kV. So 221.7 kilovolts. So this will be my base for this region. So here it will be 221.7 kilovolt will be the base. And what is the S base? S base of course will be 100 MVA for this. And therefore the line voltage also, the base will be 221.7 kV for this line. Okay. Now the issue is the 7%. This 7% is on 30 MVA base and this is all a single phase thing. So this I have to convert equivalently to the system base, that is 100 MVA by 221.7 kV. So that job we'll have to do it. So we'll come to it later. Now coming to this side. So now I can incorporate these two into one region. So let me mark that as another region. So this is my region 3, which comprises of this one. So what is the base voltage for this? So again look at the transformer. So here 221.7 kV is the line to line voltage. So I have a transformer T1. It is a star and delta. So here line to line voltage is 221.7. So therefore, what will be the phase voltage? So that it will be 227 by 3. And what is the turns ratio here? Turns ratio, if I now look at it, 20 by 150 kV. So this is 20 kV by 150 kV. So therefore, what will be the voltage induced in one of the phases in the primary side or this side? So it will be 221.7 divided by root 3. This will be the voltage of each phase, and this I will multiply with turns ratio because this and this form one transformer, that is low voltage. So I have to give 20 in the numerator and 150 in the denominator. That itself will be the line voltage on the secondary side. So let's do this calculation. 221.7 divided by square root of 3 multiplied by 20 and divided by 150. I'm getting 17.066. So I'll just approximate it to 17 kV. So this 17 kV will be the line to line base voltage here. So the procedure is always same. Any one part of the network, the base voltage is given. With the help of transformers, you keep transforming, and then since you have a delta star, star delta kind of transformers, you have to take care of extra, that root 3 factor you have to take care, and then you get the 17 kV as a base voltage here. But the generator itself is rated at 18 kV, it's okay, not a problem. The base choice will be different and the rating can be different. That is how this problem has been designed. Now, the system base again is of course 100 MVA for the entire system. Now we need to do some kind of impedance transformations. So 8% on local base, how much it will be on the system base. So for the generator. So let's look at generator 0. We all know that Z per unit in the second base will be Z per unit in the first system and then multiplied by V base 2 by V base 1 square multiplied by S base 2 by S base 1 by S base 2. So I am hoping this is correct, but then if this is wrong, things will be difficult. So let me just derive it. So this is just a guess. See, what is Z per unit? Z per unit is nothing but V base square by S base. So Z per unit 1 equal to this V base 1 by S base 1, and Z per unit 2 is nothing but V base 2 square by S base 2. And what is, I'm sorry, this is all wrong. What is Z base 1? Z base 1 is V base 1 square by S base 1, and Z base 2 is V base 2 square by S base 2, and Z actual is Z per unit 1 into Z base 1, which is also equal to Z per unit 2 into Z base 2. So therefore from this Z per unit 2 is equal to Z per unit 1 into Z base 1 by Z base 2. So which is, now I have to substitute this 2 here, that is Z per unit 1 into Z base 1. Therefore I get VB1 square by SB1 into SB2 by VB2 square. So I think the formula which I have written above is wrong, so this is the correct one. See, I don't remember this formula. Every time I come across to solve this, I just derive it myself. So this is wrong. Sorry for that, this is wrong. So let me just quickly verify that. Z base 1 is V base 1 by S base 1, Z base 2 is this, and then actual is per unit into base. So therefore from this I'll get per unit 2 will be, okay, and that's it. So alright, so let's use this formula now. Look at the generator. So the generator 8% is based on 18 kV and 100 MVA, and we want on 17 kV and 100 MVA. So how do we do that? So Z per unit for generator is equal to, it is 8%, that means I'll just keep 8%, and for generator's own voltage is 18 kV, whereas I want it for 17 kV, and this is both, so the square will be there here, 100 by 100, that's it. So let me do this, 8 into 18 by 17 square into 100 by 100, so 8.968, so 8.97%. So 8.97%. So this is per unit impedance of the generator. Alright, next look at the transformer. So for this transformer, what is the base impedance? So the base impedance will be, base impedance will be not required actually. So here it is 6%. So from 6%, here instead of 40 MVA, I will take 120 MVA because 3 into 40. And then the voltage, I should take 20 because the transformer is on the generator side. So 150 I should not take. I should take 20 kV as the voltage. And 17 kV is the required voltage. So from this, I'll get the calculation. So let me Z per unit of transformer T1. Basically it is 6% and here its own voltage is 20 kV but I require for 17 kV, and then here it is reverse. I require for 100 MVA base but it is 40 into 3, that is 120 MVA. So this is the way we convert the per unit impedance of the transformer T1. So let's do that. So 6 multiplied by 20 by 17 square and then multiplied by 100 and divided by 40 divided by 3. So I'm getting 6.92%. Alright, so let me write that here. 6.92%. Good. So I finished the first region. So I had found the equivalent impedance of this, reactance of this and this. Now let's come to the line. What is the base impedance? So VB is 221.7 and 100 MVA. So I'll get the Z base. So Z base for line is 221.7 square by, so this is kV square by 100 MVA. So these two units will cancel out each other, I'll get ohms, and this one will be 221.7 square by 100. So 221.7 into square divided by 100. 491.5. Whereas the reactance of the line is nothing but J80 given in the question. Therefore, reactance of the line in per unit will be J80 ohms divided by 491.51, which will be, so 80 divided by 491.51. 0.16276, that is 16.27%. I can express it as a percent also. 16.27%. So this is the per unit or per percent already I have mentioned. So this is for the line. Okay, so let me change the color, it's getting boring. Alright. Next, what do we have? So I finished the generator, I finished the transformer T1, I finished the line. Now coming to transformer T2. Since now I am on the primary side of the transformer because this is in this region itself, so I can use this. Now, what is the base voltage I should use? So here 160 kV is the star side. And earlier I forgot to mention 20 kV is on the delta side. So 20 kV on delta side is nothing but the phase voltage on delta will be equal to the line voltage. So I directly use the 20. But here I should be careful. 160 kV into root 3 will be the line voltage because this side is on star connection. And the line voltage here is 221.7. And S base is this. So using that, I should convert the 7% back into this. Also 30 MVA, each phase is 30 MVA. So total I have 3 phases, so it will be 60 MVA. So let me do the calculation for T2. So transformer T2. So impedance in per unit for transformer T2 is nothing but, originally it is 7%. Now the voltage So the voltage 160 kV per phase into root 3 will be the line voltage. Because the primary side is star connection, I have to multiply by root 3. Whereas my base is 221.7. So these two are not equal actually. So this is square. And then multiplied by S base. So I have to use the system base, that is 100 MVA, and whereas 30 into 3 will be the 3 transformers, 3 single phase transformers like this. So this is my entire calculation for the per unit impedance of the second transformer. Let's do that calculation. So it is 7%, 7 multiplied by 160 into root 3, 160 into square root of 3 divided by 221.7, and this entire thing I have to make square, right? And then 100 by 90 into 100 divided by 90. 30 into 3 is 90. So I am getting 12.15%. So because 7 I used as a percent, so 12.15% is the per unit reactance of the transformer T2. Okay. So transformer T2 is also done. Now finally what I am left with is the load. So this load is rated at 24 kV, and also the base voltage is also 24 kV, so no problem. And the load is represented as 40 megawatts at 0.9 power factor lag. So I can just simply write it 0.4 as because the S base is 100 MVA, so this is nothing but 0.4 per unit at 0.9 power factor lag. So that is my load. So load 40 megawatt by S base, that is 100 MVA. Because the voltage ratings are same, I don't have to consider that. So this is 0.4 per unit at 0.9 power factor lag. So this is the load. So this is actually active power. So let's calculate the 40 megawatt at 0.9 power factor lag is nothing but, so 40 by 0.9 will be my S. That will be 40 by 0.9, 44.44 MVA. And then what will be my Q? Q will be square root of S square minus P square. I'm just for the sake of completeness I'm doing this. So 44.44 square minus 40 square, and then this total will be square root. So this is 19.36, and because it is lag, so it will be plus J 19.36 MVAR. So what is my total load? So total load is 40 megawatt plus J 19.36 MVAR. So now if I write it, so it will be 0.4 plus J 0.1936 per unit. Because 100, if I divide by 100, both will be like this. So this is S per unit, my load. I think now I have completed everything. So just I have to draw the diagram. So maybe I'll use this place to draw the diagram, because I have run out of the place at the end of the page. So here I'll do that. So what is the reactance diagram? So look at the, in fact I think I can move all this. So I have a generator, transformer, line, transformer and load. That's it. So I have a generator, it's only this one, and then there is a transformer, and then there is a line, and then there is another transformer, and then finally there is a load. Now, what are the values? So we have already calculated. So let me go down here. 8.97%. So 8.97% is the reactance of the generator. What is the reactance of the first transformer? That is 6.92 and then 16.27 for the line. Okay. So this is J 6.92% and then J 16.27%. I hope it is correct. Okay. What else? I have another transformer. This another transformer, let me refer, 12.15 J 12.15%. And then finally the impedance, the S per unit is 0.4 plus J 0.1936 per unit. Is it 1936? Yes, 1936. Now also given in the question is the voltage at this bus is equal to 24 kV line to line. So now if I express the voltage in per unit, it will be actually 24 kV divided by 24 kV. So the voltage here is 1 per unit. Now I can actually find the current and find the impedance, internal impedance of this generator, internal voltage generator of the generator. So how do I find the current here? I can add all this and then I can find the current from V4 and S, and then I can find the voltage drop. I can find the voltage. So let's say, although it is not asked in the question, let's say it is asked what is the voltage at the terminals of the generator. How much voltage is to be generated so that I maintain 1 per unit at the load. So what is this voltage? So you can look at the say and say it's 18 kV. Oh, but 18 kV is the rating. But actually how much voltage we need to generate here is what is the doubt. So just take a while and then try to solve this problem. I'll do it myself. You can pause it and then try yourself. I'm going to do it myself. Okay, so how I solve this is first I'll make a copy of the diagram here. This is our reactance diagram. After all efforts, after all calculations and all, finally we got this. So let me go to a different new page. So this is the reactance diagram. And then let's represent this voltage as E1. So the question is find E1. So what voltage should the generator terminal be maintaining so that 1 per unit or 24 kV is maintained at the receiving end? So how do we find E1? Just we begin by finding the current. So what is the conjugate of current? Conjugate of current is nothing but S by V4, or I can find current itself as conjugate of S by conjugate of V4. So conjugate of S is 0.4 plus J 0.1936. Of course, this since it is conjugate, this will become minus, and then 1 conjugate. So because 1 is real number, its conjugate will also be 1. So finally the current I get is 0.4 minus J 0.1936 per unit. Now I have the current. What is the total reactance? So total reactance is the addition of all this. So let me do that here. So, or I'll do it here. So XT is my total reactance. That will be 8.97, 6.92. So 8.97 plus 6.92. I'm doing it in all in percentage values, not the per unit values, but anyway, it is both equivalent. 16.27, 16.27, these are all in series. So plus 12.15. So this is my total impedance, 44.31 percentage. So my XT is 44.31 percentage, or that's nothing but 0.4431 per unit. So what is the voltage drop? I into XT. So that is nothing but multiplication of these two. Okay. So let's do that. So 0.4431 multiplied by 0.4 minus 0.1936 I. So this is a complex number. I has to be a small number. Okay. So I got this as the voltage drop. So 0.177 minus J 0.0858. So this is my voltage drop. Okay, so how to get the E1 voltage? Nothing but voltage drop plus the sending end voltage V4. So 1 plus all this. So I'll get 1.177 minus J 0.0858 per unit. So that is nothing but, so 1 plus answer. The earlier answer, it will just add 1. So now, I'll just store it as E1 equal to answer. So now, absolute value of E1 and then angle of E1. So this angle will be in radians, so I'll convert into degrees. So I'm getting something like this. By the way, why it is coming negative? I think I need to check something here. Oh, I made a mistake. This is actually J. So the reactance is J. So when I multiply this with J, so actually this will be J and this will be the active. So I have to multiply with J. So that will be J into J is minus 1, 0.0858, and then plus J 0.177. I'm sorry for the mistake. So this is actual. So let me just correct it. I think I'll just scratch this thing. So V drop plus V4, it will be 1.0858 plus J 0.177. So per unit. Okay, now let me do that here. Let's define E1 as 1.0858 plus 0.177 I. Now I need absolute value and angle. So 1.1, 9.258 degrees. So 1.1 at an angle of 9.25 degrees. So, or 9.26 degrees, we'll round it off. So this is in per unit. So but what is the actual value of E1? So I have to multiply with the base. So now if I refer to my system here, so the V base is 17 kV in this region. So if I want to know this voltage, oh by the way, I think I have made another mistake. If I want this voltage, I should not consider the voltage drop of the transformer, the generator. So the reactance of the generator should not be considered. So this 8.97 should not be considered. So I am actually calculating this voltage. So that is internal voltage of the generator. So anyway, I think you get the idea. So what is the internal voltage of the generator? So the internal voltage of the generator is 1.1 into 17 kilovolts at an angle of 9.26 degrees. that is nothing but 17 into 1.1. So 18.7 kilovolt with an angle of 9.26. So this is the internal voltage of the generator. And if you are interested in terminal voltage of the generator, you can always calculate that. So again, go back here to find the drop. So the drop will be 8.97% multiplied by the current, and that drop you add it to this and you will find the E1. So strictly speaking, E1 is here, this is E2. So we calculated E1. So I leave it for you to do it as a homework. So I think in this video I try to show how to handle three-phase star delta kind of connections in your system. So basically through this problem and through the earlier problems, I hope you have got some idea about how to solve these kind of things. So if you have any doubts or any comments, please leave it in the comment section. And thanks for watching.